Welcome to Chapter 5 of our calculus journey. We had just looked in Chapter 4 at applications of derivatives, and the very last section of Chapter 4 is going to be so important to us on how you take an antiderivative here in Chapter 5. So we're going to start by kind of doing some theoretical stuff that kind of tries to link all this everything together that we've been doing, and what is the true meaning of doing an antiderivative. So many argue that this chapter is the cornerstone of calculus because it explains the relationship between the two processes of calculus, which is differentiation and integration. So in this chapter we will develop key properties of definite integrals, investigate a few of their many applications, and present the first of several powerful techniques on how to take and evaluate definite integrals. Now, the derivative of a function is associated with rates of change and slopes of tangent lines. We've talked about that all semester long. We also know that antiderivatives, or the indefinite integral, which is the reverse of the derivative operation. So when we were in section 49, we were going backwards of taking the derivative and figure out, okay, if I had the derivative, what would I have had originally in order to get this derivative? So what does the geometric mean behind integrals? And the answer is very, very powerful. It is here with the area under the curve. That is going to be the meaning of that integral. And so we're going to kind of investigate first the area under a velocity curve, and we're just going to start off real basic. Where I have a constant velocity. Well, of course, we all know that when we're driving or something is flying through the air, that the velocity of it is not always constant. But in order to get our idea across, we want to go down to the basics. So, consider an object moving along a line with a known position function. We learned in previous chapters that the slope of the line tangent to the graph of the position function at a certain time gives the velocity at that time. So when we have graphs of derivatives, that would be a graph of a velocity function. We now turn this situation around. If we know the velocity function of a moving object, what can we learn about its position function? Now, imagine a car that's traveling at a constant speed or a constant velocity of 60 miles per hour along a straight highway over a 2-hour period. So very, very basic. You're at a constant 60 for 2 hours on a straight highway. So think about going on the interstate maybe and setting your cruise at 60 for 2 hours. So let's graph this. Looking at a graph of this, I'm going to do my time down here, and we're in hours, and then I'm going to put my velocity across here, and that is in miles per hour. And then a room there. If we have a constant velocity over a 2-hour period, so call this 1, call this 2, then a constant it's always going to be just a flat curve. It's never changing. So I'm going to go kind of by 20s maybe, make this 60, and this to be my velocity function for 2 hours. We're going to say v equals 60 here. And that is the velocity curve for a constant velocity of 60 miles per hour for 2 hours. So, if we talk about, well, if I'm going 60 miles per hour for 2 hours, how many miles have I traveled? That's what we refer to also as displacement, or the distance. Well, there's a common formula that you should know about displacement or distance. That distance is equal to rate times time, and we can easily, by a multiplication operation, find out what our distance is. So I would take my 60 times the time of 2, which would give me 120 miles that I would travel for that time period. Now, why is that significant here in this most basic case when we're talking about the area under a curve as the meaning of the integral? Well, if I look at my curve here, it is a flat curve. If I cut that guy off, say right here at t equaling 2, notice what I've just created, if my axis was a little bit more straighter, but I've just created a rectangle. And if I ask you to find the area of that rectangle, we would take our length times our width. That is the 2 times the 60, which would in turn give me the distance that I have right over here as 120. So here is what we want to do. This product is the area of that rectangle that's formed by our velocity curve and our t-axis. So this is our t-axis between 0 and 2. In this case, we see that the area between the velocity, that v equaling 60, and the t-axis, so I stopped here at my t-axis, I did everything in between that velocity curve and the t-axis, is the displacement or the distance of the moving object. So now, because objects don't necessarily move into a constant velocity, we can extend this idea to positive velocities that change over an interval of time. So calculus is able to allow us that if I have a velocity curve that may look something like that, I can now find the distance that that object has traveled over time by finding the area under that curve. Okay, so that is big, it's huge. Okay, so here's a strategy that we're going to take in order to find some of these areas here at the start. We're going to divide our time interval into many subintervals. So instead of going from 0 to 2, maybe I go from 0 to a half, and a half to 1, and 1 to 1.5, and 1.5 to 2. We're going to approximate the velocity of each of those subintervals with a constant velocity, and then we're going to find the displacement of each subinterval, aka the area of the rectangle that's created, after I've created a rectangle here in step 2. Most of the time, actually, maybe I should try a vertical one. It could be like that. It could be a vertical one like this. And then what we're going to do is we're going to add up all those areas. Okay? So we're going to add up all the areas that we find underneath our curve. So this will produce an approximation to our displacement, or an approximation to the area under the curve. However, this approximation generally improves as the number of subintervals increase. And we're going to see that here in just this example that we have here. So suppose the velocity in meters per second of an object moving along a line is given by this quadratic function, t squared, where t is in between 0 and 8, that's on our t-axis, and we're going to approximate the displacement, the area under the curve, using some rectangles, of the object by dividing the time interval into subintervals of equal length of 2 and then of 4. So we're going to approximate the velocity with a constant value to the value of v evaluated at the midpoint. Okay, so this is going to be important for you to have a reference of where we're going to do the approximation from. So let me tell you how we're going to split up our interval, and then we'll talk about the midpoint part. All right, so let's just graph this, okay? I'm going to go from 0 to 8, and then if you were to do some values here with that t squared, when you get to 8, it's going to be at 64, 7 is 49, da-da-da-da-da. So I'm just going to approximate with that parabola that it looks something like that. You can do a more accurate graph, but here we just need some approximations, okay? All right, so if I have this quadratic that I want to approximate, if this is my velocity, and I have just established in the earlier example that if I find the area under this curve, that is equivalent to the distance that this object travels from 0 to 8, okay? Now, my subinterval here that I've covered up, I want to do it in 2 subintervals, okay? Well, I have an interval from 0 to 8. If I need to cut that in half to make 2, then that means I need to go from 0 to 4, and then from 4 to 8. Okay, an easy way to figure that out, and I'll show you here in a little bit with the formula, is to take the difference in your interval and divide it by the number of subintervals. What is the length of each interval? That would be what you find there. So this is a length of 4, that's a length of 4. All right, now here's where I want to approximate a rectangle. Okay, it's not going to be exactly like what we saw up here with this velocity function because it is a straight line up here that would create a rectangle. we are going to create rectangles on our own, okay, and then add them all up to get our approximation. So I need to create a rectangle here, but my reference point, they're telling me, is to use the midpoint of my interval. So from 0 to 4, midpoint, you can add them together and divide by 2, but this one's pretty easy to realize that the midpoint is at 2. So what means I need to go up here to this function value at t equaling 2, and I'm going to create a rectangle from 0 to 4, and I'm going to now find the area of this rectangle. Maybe let me change colors so you can see that. I'm going to find the area of this rectangle and use it as an approximation for the displacement of this object. Now, from my interval from 4 to 8, where is the midpoint of that? The midpoint is at 6, so I need to travel up to my function value, and I'm going to create a rectangle, and sometimes it's hard to envision these rectangles, but I'm going to create that rectangle, and I'm going to find the area of each of these, add them up, and that's going to be my approximation. Now notice, why is it an approximation? Well, I've got this overhang here. I've got this piece that's not even accounted for, and I have this overhang here that's outside of that function. And so it is not going to be exact, but that is to come we have our calculus, okay? So how do I find the area? Well, we're going to be finding the area of rectangles, which is, area is going to be, or displacement, we're actually finding displacement here, but it's technically the area. We're going to take the width times the length plus the width times the length of each one of those rectangles. So I'm going to change it here. It's not really area. This is for the displacement, since this is actually a velocity curve. We can put meaning to it. So I'm going to take the length times the width of this, or the width times the length. Either way, it doesn't matter which order. So I have 4 times whatever this is. Well, that is matching up with the function value at my midpoint, which is 2. So the length here is going to be 4, but I need to use my function, v equaling t squared, to find this value, which is this length right here. So at t equaling 2, if I plug that into my function, that gives me this length here. So that means I need my function, plug in 2, gives me 2 squared. Then I want to do the same for the next one. What is my width here? That distance is 4. What is the height, or the length of that rectangle? That means that I need to find the function value at t equaling 6. Those are the important values that I have here. Plug in 6 to my function, and I get 6 squared. And now it's just operations that you have to do, okay? Doing some number sense here. This 4 times, this becomes 4 is 16. Then I get 36 times 4 gives me 144. So the displacement of this object from 0 to 8 is 160 meters using a subinterval of 2, okay, where you have 2 rectangles that you're adding up. Now, what happens if I change that subinterval? And now I want not 2 rectangles to add up, but 4 rectangles to add up, okay? So we can do the same type of thing. Okay, and I approximate my v equaling t squared, and I can now from 0 to 8 divide it into 4 rectangles. Well, how wide is each one of those rectangles? Again, take the difference in your distance here and divide it by the number of subintervals that you need, and that tells me that for every 2 seconds I need another rectangle. So that means I need to go from 0 to 2, then from 2 to 4, 4 to 6, and 6 to 8. And I'm going to grab the midpoints of each one of those intervals to make my rectangles, okay? So from 0 to 2, I'm going to change colors here so you can see that. For 0 to 2, my midpoint is 1. The function value is right there. And I'm going to create a rectangle from 0 to 1, okay? From 2 to 4, the midpoint is at 3. So I need this function value to get my height of my rectangle. And so from 2 to 4, I'm going to find the area of this rectangle and add it to the first one. Then from here to here, my midpoint is 5. So I'm going to create the rectangle that is formed by t equaling 5 in the function. And lastly, at 7, I'm going to create that rectangle. And these are the rectangles that I need to find the area of in order to approximate the displacement for this function. So the displacement, again, is going to be the area of each one of those rectangles. So let's do that. I have a width, or a length, times a width. So I have a length of 2 this time that I want to times by the height of that, which is, again, on the function b equaling t squared. But this time I'm using t equaling 1. So I'm going to go 2 times 1 squared. You should see a lot of patterns going on here. So once you kind of get the pattern, just continue that pattern. Then I'm going to turn to this rectangle, which my width, again, is 2. I got that right here for all of them. It's going to be the same. Then my height is when v is equal to, or the t is equal to 3 in my v function. So I'm going to plug 3 in there and square it. Then I'm going to get a width of 2 again. I'm going to use 5, plug it into the function and square it. Then for my last one, I have a width of 2 and using 7 as the midpoint, plug it into my function and square it. So now again, it's just some operation of numbers. And when I run down the line of what these are, I get 2 plus 18 plus 50 plus 98. And that sum for this displacement is 168 meters. So notice the numbers change. But what do I know about the approximation as I increase the number of rectangles? Notice here there's not very much missing. This is a smaller amount. There's not very much missing in these pieces, but these can kind of cover. What we find is as the n increases, then the area gets to be more exact. So the idea of this will come later as to how that we find the exact area. But for now, let's kind of investigate what we have here. Look at what happens. I gave you this chart. As if I increase my subintervals. Now here we did 2 and 4. But what happens if I have 64 rectangles? The length is going to be 0.125 seconds across there for that rectangle. But notice, look at what happens to the area under that curve, or the displacement for this function. Well, it's kind of like it's limiting to 170.65, and that's the beauty of calculus, where we're actually bringing in the idea of a limit to be able to take care of this area under the curve. Okay, so now let's look at this with an interactive tool. And so I just pulled something up off the internet which kind of shows this. It's off of mathworld.wolfram.com. And so here's a function that we have, and I've represented it by having 2 rectangles approximate the area under this curve with the x-axis. So here this one has kind of above and below for those, but I could actually, let me change this. Let's go to do our t squared. And I'm going to say that it goes from our interval, and I'm just going to go -1 here to 9, so we can kind of see a little bit more of that. Let's replot and see what it gives us. Okay, maybe not. So let's go back. I'll just bring it up again. Okay, and use that function. So if I were to kind of use this function as well, and I'm going to approximate it with 2 rectangles, then notice that the area outside from underneath this curve, this Gillett little thing here and this piece here, there's some gray area that's over, so it's kind of an overestimate of that curve. But what happens if I go to 4 rectangles? 4 rectangles along here. This one's awfully small. This one is a little bit more, but I still have some stuff missing. What if I choose 10 rectangles? 10 rectangles is getting better, where I end up having smaller. What if I end up choosing 20 rectangles? And I replot that. Notice now what's happening as those rectangles are getting smaller and smaller is that the amount of excess around my function is getting smaller and smaller as well. What if I choose 30 rectangles? Notice there it's even smaller. So hopefully this is a visual for you. Let's see if it'll do 50. A visual for you to see that, and it's actually using a midpoint approximation here, that now this is pretty good. What if I do 100? Notice there's hardly any excess that I have now, and then there's even less when I choose 100 rectangles. So there's something here that we could do a left endpoint as well, instead of using the midpoint. Notice that here the estimated area is very, very close to the actual area. If I have a right endpoint, basically I would just go off of the right endpoint of the interval to create the rectangle, and then we can go back to kind of our midpoint. And so there you don't see much difference on the picture itself, but you do see a little bit of difference in the estimated area, which is where we're going to go next. Okay? Okay, so back to our notes. We wouldn't spend much time investigating areas under curves if the idea applied only to computing displacement. That's what we were looking at on our velocity curves. But this finding the area under curves arises frequently and turns out to be immensely important. And we will see that throughout Chapter 5. Now, hence, this is why we're going to do a systematic method to approximate the areas under curves. And so here we get with our one of our big definitions for this section. And they're called Riemann sums. Now, consider that we have a curve. And I just have some curve that goes like this. Now it's not that constant velocity function. And I have an interval from A, actually let me just, to B, do solid. And I want to find the area under this curve. We're going to call that for region R. Okay? So what we were doing before to find, we're going to call it delta x. For the length of each subinterval, and I kind of alluded to that of the first example where I was taking the 8 minus 0 and dividing by n. That is the b minus a over n will give me the width, or actually the length of each subinterval. So therefore, I'm getting ahead of myself, delta x is going to be the width of our rectangle. Okay? Now, the kth grid point. Grid points are all these points along the bottom that we use to find these rectangles. Now, I'm going to call this x sub 0, and then we're going to have all these other little grid points along here, okay? I'm going to do dot, dot, dot type thing, because there could be multiple ones, like we showed on that interactive tool, where we could go up to 100 rectangles at a time. So we're going to call this x sub 1, x sub 2, x sub 3, x sub 4, and then I'm going to call this x sub n minus 1, where our last endpoint I'm going to refer to as x sub n. So when I pick one in the middle, we're going to call that the kth grid point. So x sub k is what we're going to call that. And in order to figure out where that is, it is a combination of where we start at A and adding like a distance of that delta x. Here's 1 delta x, here's 2 delta x, here's 3 delta x. So we're going to write that as A plus k times delta x, where k is going to equal 1, 2, all the way up into n. Okay, so I can have different iterations there for that. Now, in order to find the area of a rectangle that I create, and again, we can kind of jot some of those rectangles down if you want. Here, we used the midpoint before. I'm going to use the left-hand endpoint on this one and create a rectangle. Come up here on this interval from x sub 1 to x sub 2, create a rectangle from where it is on the function. Here's my function value there, create a rectangle. Here's my function value here, and create a rectangle. So you can see I'm subdividing that region. And so, how do we find the height of our rectangle? Well, the width comes from b minus a over n. But it is determined by some of these grid values on the function. That's what's determining the height there of that. So, to find the height of each rectangle, you need to remember that it correlates to the function value at, we're going to call it x sub k, x sub 1, x sub 2, x sub 3. And so in order to find the area of one rectangle, it can be represented by our height times our base, or our length times our width, or the base times the height, however you want to put it. But the height of that is created by the function value at x sub k times the width of each rectangle, which is created by that delta x. And so this is kind of mathematically a formula that we could use in order to find the area of those rectangles. Okay? And here's kind of our culmination, our big idea for this section. I should say base. Okay? Suppose that f is defined on a closed interval AB, which is divided into n subintervals of equal length, call it delta x. If our kth grid point, x sub k, is any point in the kth subinterval, which can be referred to mathematically as x sub k minus 1, comma x sub k on that closed interval, for k equaling 1, 2, all the way up to n, then the area under that curve is approximated by the sum of x sub, and we're going to start by x sub 1. These are kind of, don't lock in that this is always x sub 1, times delta x plus f of x sub 2 times delta x plus f of x sub n times delta x. And so basically I'm going to take, this is representing one area of a rectangle, this is another area of a rectangle, this is another area of a rectangle, and I'm going to add them all up. And that's what we refer to as a Riemann sum for the function f on the interval of AB. Now, here's why I told you not to get too caught up on these x sub 1s always starting here, because that could be x sub 0, which if I'm using a left-hand rectangle created by starting here, then I need x sub 0. So don't get too caught up on the subscripts, because if I have a left Riemann sum, that is if x sub k is the left endpoint of the interval. We also can refer to a right Riemann sum if x sub k is the right endpoint of an interval. And the one we already looked at was looking at a midpoint Riemann sum if x sub k is the midpoint of the interval for k equaling 1, 2, all the way till n. Okay? So you may want to make note, we did put delta x up here, but you also may want to just put that all in one spot. Remind yourself that delta x is b minus a over n. Okay? So those are the things that we're going to need in order to find a Riemann sum. Again, a Riemann sum is something that's going to approximate the area under the curve. So let's talk about the different types of Riemann sums here. Okay? Here we have, and they start with x sub 1 again. The subscripts, don't get too caught up with them, okay? This is representing wherever your first one's going to be. The left Riemann sum is you take the left interval from A to here, and the left-hand endpoint, you find the function value and create the rectangle. Again, on this interval, we're going to go on the left-hand endpoint up to the function and create the height of that rectangle. For this interval right here, the left-hand endpoint to create the rectangle there for that. Now, if I do a right Riemann sum, I'm not going to start at A. I'm going to start at the next grid point. So that means I'm going to go to the right-hand part of that interval, go up, and create the rectangle. So in this case, you almost have to kind of go backwards. Find the function value on the right-hand endpoint and come backwards and create that rectangle. Find the right-hand endpoint, come backwards, and create that rectangle. Okay, so that's a right Riemann sum. Notice that here is our delta x. That's our width of our rectangle, and the height that's going to be determined about the f of x sub 3 would be what this height is for this function. The midpoint Riemann sum is kind of what we talked about before, where in this interval, find the midpoint, find that function value, and create the rectangle. Find the midpoint of this interval. Up on the function, create the rectangle that's around for that interval. So there's 3 different kinds. And we're going to try to work with each one here for this example. We're going to let R be a region bounded by our function 3 square roots of x on the x-axis between x equaling 4 and x equaling 16. We want to approximate the area of that region under using a left Riemann sum with n equaling 6 subintervals. And then they're asking us, does this approximation underestimate or overestimate the actual area under the curve? Okay, So we are going to first always draw a picture. Okay? So I'm going to draw my picture here. Now, a square root of x is something like this. So we don't need to do exact. We're just doing approximations here. Okay? So this is my square root of x, and I'm going from 4 to 16. Now, I need 6 subintervals. So what is the width of each subinterval? Well, that is taking 16 minus 4 and dividing by 6. That b minus a over n. That's our delta x. I'm trying to squeeze it in here. So this gives me 12 over 6, which is 2. So that means that for every 2 spots, I need another subinterval. So I'm going to go 4, 6, 8, 10, 12, 14, 16. So I'm going to extend that a little bit. Okay, so we want a left Riemann sum. That means I'm going to start at A, and I'm going to go up to my function, find that point, and I'm going to create a rectangle up until the next grid point, which is 6. At 6, I'm going to find my function value, and I'm going to create the rectangle on the left-hand side of that interval to find the next one. And I continue that at 8, at 10, at 12, and at 14. Okay? So it's all dependent upon each one of these grid values. Okay? So we could call this x sub 0, x sub 1, 2, 3, 4, 5. Or you could call it x sub 1, x sub 2, 3, 4, 5, 6. I don't care. Remember, don't get caught up on those subscripts. We want to get the idea down of what is the area under this curve. So the area has to be approximated by the area of these rectangles. So I need my width times my height. Remember, that is f of x sub 1. Oh, actually, hang on. Let me revert back. Let's not put the x. We'll save a line, okay? Which value in 4 to 6 did I use to create my rectangle? I created the x equaling 4. So I'm going to do the function value at 4 times my delta x. Then I created this next rectangle using x equaling 6, which is the left-hand endpoint of that interval. So I need f of 6 delta x. And I need to continue that all the way through x equaling 14. So f of 8 delta x, f of 10 delta x, f of 12 delta x, and f of 14 delta x. And I told you there's a lot of patterns going on here. It's a lot of writing sometimes, but this is so good for the foundation of these Riemann sums. All right, so what is the function value at x equaling 4? Well, I got to use my functions. I'm going to throw 4 in there. So that means I get 3 square roots of 4 times delta x. What is the width of my interval? Well, we found it out right here. That is 2. Then I need to put 6 into my function and times it by my delta x. Then I need to put 8 into my function and times it by delta x. 10, 12, and 14. Now, it's nice that this is a very small function. I don't have to worry too much about writing a whole lot. But you can, you don't have to write this fully out. You can plug them in, your calculator if it's a longer function and just put that number times your delta x. So now what I'm going to do, and throw all of this into my calculator and figure out what the approximation is for this area under the curve. And when you do that, I will tell you it's 105.876. Now, the question that we have is, does the area approximation underestimate or overestimate the actual area under the curve? Well, look at your picture. We have all of this missing that I'm not accounting. Well, sorry, that's not my interval. Never mind. I have this missing. I have this missing. I have this missing. And so it's not the exact area. It would be if I had all of that colored in. Well, I'm not quite there yet. Therefore, this underestimates the area of the curve. Okay? I always answer that question by looking at my picture. That's why a picture is so important. Okay? Now, I'm going to do this same thing, but this time I'm going to do a right Riemann sum. So I'm going to go from 4, and again, if I do 16 minus 4 all over 6, because I want 6 subintervals, this time we're doing a right Riemann sum. this is still going to be every 2, so I have 4, 6, 8, 10, 12, 14, 16. Okay, I need to create the right Riemann sum, which is found by looking at my first interval. I need the right-hand endpoint go up to my function, and I'm going to create the rectangle from there. I'm going to my right endpoint of my next interval, go up to my function, and create the rectangle from there. At 10, at 12, at 14, and at 16. That's the last interval, so I have to include this 16 this time. The one that I'm not including on this interval this time in my function is going to be 4, because I don't start at 4. I start at the 6 and then go to 8, 10, 12, 14, and 16. So to find the area approximation under that curve, I need the function value for this height of this rectangle is going to come from plugging 6 in, and it's driven by that. So I need f of 6 times my delta x. Plus, the next one was 8. I used 8, so I need f of 8 delta x. I'm going to continue that through to 16. Okay, again, I told you some of this might be a little bit of writing, but again, it's building our foundation. So if I plug 6 into my function, which was 3 square roots of 6, and then times it by my delta x, which is 2, then I'm going to do the same with 8, with 10, with 12, 14, and 16. And so, again, this is the idea. The length times the width of the rectangles and add them all up. I will tell you that if you plug this into your calculator, you now will get 117.876. And to answer the question, does this overestimate or underestimate the actual area under the curve? And notice here I've got excess, and each of those that's above that curve. So that area of 117.86 overestimates the actual area there. Again, having that picture is very, very important. Now, maybe we don't draw the picture the next time, but could I figure out the area noticing here using this picture? Now I want to use the midpoint Riemann sum, still having the same number of subintervals, and so the area here would be found by using the the midpoint of each of these subintervals. So the midpoint here is 5, 7, 9, 11, 13, and 15. So I need f of 5 delta x plus f of 7 delta x plus f of 9 delta x plus f of 11 delta x plus f of 13 delta x plus f of 15 delta x along that way. And so the same idea happens. I need to find the function value into my function, and so I'm going to get 3 square roots of 5 times 2 plus 3 square roots of 7 times 2 plus 3 square roots of 9 times 2 plus 3 square roots of 11 times 2 plus 3 square roots of 13 times 2 plus 3 square roots of 15 times 2. And so notice this is important. I know it's tedious to write all that out sometimes, but this is important to be able to show your work when doing a Riemann sum, okay? So the approximation that we have here is going to be 112.062. That's what we get when we find the midpoint. And if we were to draw that with the midpoint, you would find that there would be even less excess on those. So that's why it's kind of hard to determine, is there going to be an overestimate or an underestimate using the midpoint. But if I tell you that the actual area for this curve 3 square roots of x from 4 to 16 is 112, which we will know how to find that later, which one of our Riemann sums is the best approximation to that 112? Well, we had 105, we had 117. Obviously, this one down here is our best approximation, and that is the midpoint Riemann sum. It's the best approximation for the curve, the area under that curve. Now, I know that this writing and some of this can kind of get tedious, but is there another way to do a Riemann sum? To do Riemann sum is to factor out the width, since it is the same for each rectangle. So notice I have a delta x, all the way down to another delta x down here, and I'm timesing by 2, timesing by 2, timesing by 2. So if we were to factor that out, and then just look at the function values at each of my grid point, then sometimes that eliminates some of the writing as well. So you'll see me do some of that sometimes for that. All right, very good. Now our last little piece here in section 5.1 is to talk about sigma notation. And sigma notation is going to be important when we start finding exact values of these areas, okay? So working with Riemann sums is cumbersome with large number of intervals. So if I were to say my intervals go from 6 to 10, that means I'm going to have 10 of these areas that I have to add up. And therefore, we pause for a moment to introduce some notation that simplifies our work, in which we call it a sigma notation or summation notation, is used to express sums in a compact way. So, for example, if I wanted to add up the first 10 numbers, or the first 10 positive integers, it takes a lot to write all this out, and don't mess up. So if I wanted to do that and find the sum, I could do that, but that's a lot of writing to show that I'm adding up the first 10 positive integers in our number set. I can simplify that using sigma notation. There's a sigma for you, Greek letter. And I can say I want to go from 1 to 10 of k. So this is kind of an increment type thing where I'm going to start with k equaling 1. I'm going to go all the way to 10. And this is going to tell me what I'm going to do. I'm going to plug 1 in here. And then I'm going to plug 2 in there, plug 3 in there, plug 4 in there. So k is a little bit basic, but if I did like 3k minus 5, I would plug 1 in there, times it by 3, and minus 5. Plug that, figure out that number, then plug 2 in, then plug 3 in, all the way to 10, and add up all of those, okay? So this is what we like to use when we are simplifying our summations, where we're summing things up. So here's my sigma. Let's talk about some terms that I have here. So let's talk about our numbers on the upper and lower, okay? So this is what we call the lower limit of our summation. This guy would obviously then be my upper limit. This, point to here, is our sigma, which is the Greek capital letter S. That's where that comes from. Sigma for sum would be another way to remember it. This is our summan, and that is what we're using to find the sums. Okay, so just some terms for you on that. Here's some examples. What if I want to sum from k equals 1 to 99 of k? Well, what does that mean? Sigma of k equal 1 to 99 of k means I'm going to plug 1 in for k, then I'm going to plug 2 in, 3 in, 4 in. So what I'm really doing is now adding the first 99 positive integers. Now, obviously, I don't want to write from 1 to 99 all the way out, so we mathematically condense that down to a nice notation. That is going to be 4950. Now, you've got modes and calculators that can help you with summations, so you just have to know for your specific calculator how to work that. If you have a graphing calculator, it's under the math option if it's a TI. So if I want from k equaling 1 to n of k, what does that look like? Well, that means I'm adding up the first n integers, and here we don't really know where n is, so we symbolize that by one of these dot, dot, dot things, okay? And this will be important. We'll kind of see that here in just a second, what that is equivalent to. Now, what if I want to go changing up my lower limit to 0 this time, from 0 to 3 of k squared? Well, that means I plug 0 in and I square it. Then I go to the next one. I plug 1 in and I square it. Then I plug 2 in and square it. And then I'm stopping at 3 because that's my upper limit and square it. So if I add up all of these now, we get a sum of 14. And the last one I want to show you is that if I start at k equaling 1 to 4, of, say, 2k plus 1. That's my sub-n this time. And so here I'm going to plug 1 in, times it by 2, and add 1, which gives me a 3. When I plug 2 in, 2 times 2 is 4 plus 1 is a 5. When I plug 3 in, I get a 7. When I plug 4 in, I get a 9. Again, a lot of pattern work here as well. And so when you add up all those numbers, you do get 24. Okay? Now, the index that I use here, I should have switched things up a little bit instead of using K's all the time. You can use M's. I see a lot of books that have I's or J's or something like that instead of the K's. And we refer to that as a dummy variable because it doesn't matter what letter that you use, okay? It has no meaning to it whatsoever. It's just a way for us to kind of keep ourselves intact. Okay. All right, so there are some properties that I want to give you, and then we're going to work with a couple summations to figure out what is the actual sum using these properties. So suppose that we have a set a sub 1, a sub 2, all the way to a sub n, and a set b sub 1, b sub 2, all the way to b sub n, are two sets of real numbers, and suppose that c is a real number. Now, for this summation stuff, if I'm going to sum from k equaling 1 to n of a constant times a sub k, again, here these variables must match, then I can, it's kind of like our delta x, it's on each one. So I can take that constant and bring it out front, do the summing, and then multiply it by that constant just one time. So this property says I can pull that c out front, which you'll see a lot of times. We can do that also with integration as well. With limits, we can do that as well. And then our addition rule basically says that if I go from 1 to n and I have, say, a sub k and I'm adding b sub k to that of two different numbers, then the addition rule says that I can split that up. So I can just do all the k's, then I can do all the a's, excuse me, and then I can do all the b's, and then I can add up those two sums. So you're going to get a sum here of all the a's, a sum of all the b's, and then add them up. Now, this says addition rule, but you can also do it for subtraction. So if you want to put a minus there, that's fine as well. Now, here's where it's important to know what these summations are equal to. And these can all be proven. A lot of times in an upper level math class, you'll prove these things as well. But if we want n to be a positive number and c to be a real number, what happens if I sum up the first n objects of a constant? Okay, so I have 5. Now, there's no k here. So if I have a 5 there, that means I'm going to be adding 5 each time n times. Well, that's just a straight multiplication problem where I take that constant and I multiply it by the number of times I'm adding it. So that property says from k equaling 1 to n of c is equal to cn. What happens about that k? If I add up the first n integers, okay, where I do 1 plus 2 plus 3 plus 4 plus 5, obviously we don't want to add them all up. We're going to have a formula that we can use. It is going to be equivalent to taking your n times n plus 1 and dividing by 2. I'll give you 2 more of those of a k squared and a k cubed. So if we do k squared and I put 1 in and square it, 2 in and square it, 3 in and square it, all the way up to n and square it, then what is going to be the sum of that? The formula for that would be n times n plus 1 times 2n plus 1 all over 6. And our last property that I want you to know is the k cubed one, and that is simply the square of each one of these. Now, I'm not sure why that is. I might need to investigate that a little bit, but it is. That's the way I remember it, okay? So, square each one of those, you get your k cubed. Here you have multiples there to figure that out. So let's do it on a finite version because in the next section we're going to be using these n's in order to find exact areas using a Riemann sum. But what if I have n given to you, okay? How can we find the sum of this? Obviously I don't want to put 1, 2, all the way up to 45 and add them all up. We're going to use these properties to help us out. Alright, first thing I can do with our properties is that I can separate each one of these by the addition property, right there. Okay, it works with subtraction as well. So I'm going to separate those. But notice
I have a constant here with my k. And that's another one of our properties up here, that if I have a constant with my variable of k, I can pull that constant out front. So that's what I'm going to do with this 5, and I'm going to split up the subtraction. So I'm going to kind of do 2 steps in one here. I'm going to bring the 5 out, and I'm going to kind of distribute that sigma into there so I just get my k, minus, I don't have a k there, but I do have a 1, so I don't have a number really to pull out. K equals 1 to n of that 1. So here's my 5k minus 1. I've just used my properties to split it up. And the reason that I'm doing that is because now I have this sigma that is represented by this formula where I take my n times n plus 1 and divide by 2. Well, what is, whoops, I don't need to put n there. Excuse me. Find my eraser. Get rid of those n's because there actually is a number there. So we have to 45, to 45. So now I have the 5, but this whole thing right here, I'm going to use that n times n plus 1. So my n is 45, my n plus 1 is 46, and I'm going to divide that by 2. Again, I get that straight from this property that I have here. Then I'm going to subtract. What do we have here? We have a constant. So I'm coming up here to my sigma of a constant, and then what this is telling me, I have to take my constant times my n. So I'm going to subtract 1 times my n, which is 45. And from here, it's just operating. Okay, multiply 45 times 46 times 5 and divide by 2. You can cancel some things out to make it a little bit easier. No matter which way that you do it, you get 5,175. This is 45 that I need to subtract. So 5,130 would be my summation for this demand from k equaling 1 to 45. Okay? Now we have a dummy variable of m. And we're going to break this apart using our summation properties to figure out what this sum is all the way of these 45 numbers. So notice I have a constant that I'm going to bring out in front of that summation each time. So I have that 3, and I'm going to split up the sums here. So k equaling 1 to 35 of m squared. Then I'm going to bring the 2 out of the summation of k equaling 1 to 35 of just the m. Whoops, this should be an m, sorry. You start changing things up, I forget to change them. Then I'm going to sum from m equaling 1 to 35 of just the constant that's at the end. And so again, I'm going to make use of these properties that I have here to figure out what is the sum of this m squared, what is the sum of the m, and what is the sum of that constant. So I have the 3 out front. Now let's go to the squared one. Here's my squared one. I need n, which is 35, times n plus 1, which is 36, times 2n plus 1. Well, 2 times 35 is 70, plus 1 is 71. So I need to multiply by 71 and then divide by 6. Then I'm going to add on to that 2. I'm going to go to my linear one of just an m, or in this case a k. Here is the summation of that. It's going to be my n, which is 35, times n plus 1, which is 36, all over 2. And of my constant, I'm going to use this property right here and take that constant times the n, which is 5 times 35. And when I figure all that out with my numbers, that will be the sum. So 3 will cancel into 6 twice. 2 can go into 36, so you could technically do 35 times 18 times 71. However that you do it, you get 44,730. Add to that, your 2's can cancel, so just multiply 35 by 36 and get 1260. And then 5 times 35 is 175. When you add all those up, gives us 46,125 is the sum of that problem. So, good little section here, a lot within section 1, a lot of foundation material in section 1 and section 2 here in chapter 5. So, it's some good stuff. Don't forget about the Riemann sums. There are 3, a left, a right, and a midpoint. It is all dependent upon what value that you plug into that function as to which Riemann sum that you're doing. So watch that and then practice some of these summations, and that'll get us set for section 5. So chapter 5, section 2. So until next time.